Right, second question. An electron acquires this much kinetic energy when it is accelerated by an electric field from plate A to plate B. Then first, what is the potential difference between the plates and which plate is at the higher potential? And then second question asks us what are the plate separation based on the electric field strength given to be that value. Okay. So we're going to use the same formulas as in the first question. Let's just write them at the top again. The change in electric potential energy is equal to, or when a charge moves from point A to point B, is equal to Q times the potential difference going from A to B, which is equal to minus the work done by the electric field on the charge going from A to B. Right. Okay, so this question 2A. Right, okay, so let's start by making a little sketch of what's happening. So we've got our two plates. This is plate A. This is plate B. And an electron is accelerated between the two plates from plate A to plate B. So let's say it starts there at A and it goes to point B. Okay, now it asks what is the potential difference. So we're after this VBA, the change VB minus VA. So we're after this VBA, which is going to be equal to VB minus VA. Right. And then the second question is which plate is at the higher potential. Now, what is this charge Q? Q is an electron. It has negative charge, and as discussed in the first video, they like to go from lower to higher potential. So I can immediately answer the second part of the question, which plate is the higher potential, by just saying that the electron will go from lower to higher potential. So we can immediately say from that, so plate B is at a higher potential. Okay, so you can immediately answer the second part of the question. Okay, but now for what the actual potential difference is, from which you'll also be able to see that plate B is a higher potential. Right, what do I need? I need to change, let's say I want to use this formula to get VBA, and what am I given? I'm given the change in kinetic energy. I'm given the change in kinetic energy, and it is the 7.45 times 10 to the minus 17 value. Right, now how can I relate it to these equations? Now, the change in kinetic energy will be equal to the net work done on the particle, which in this case will just be the work done by electric field on the particle, which according to this is equal to minus Q VBA. In other words, VBA, which is what I am after, is equal to the change in kinetic energy over minus Q. Right, and now let's just substitute for values. Right, so what's the change in kinetic energy? Is it plus that value or minus that value that was given? Well, an electron acquires this much kinetic energy, so it gains this much. So the change in kinetic energy is positive, and it's equal to plus that value. So 7.45 times 10 to the minus 17 joules. Over, now just minus Q, and what is Q? Q is the charge of the, it's an electron, so it is minus 1.6. I'd rather use 4 significant figures than just 3, than just 2, because the data I'm given, the value I'm given in the problem has more than 2 significant figures, so it's better to use 4 rather than 2 significant figures. Coulombs, right, and now we just calculate that. 7.45, okay, minuses will cancel, minus 1.602 equals time 10 to the what, minus 17 minus 19, so this is to the power 2. Okay, and that is, there we've got our value, and it is plus, I don't have to write the plus, I'm just writing it to highlight it, plus 465 volts. Okay, so from there, from this you can also see that plate B is at the higher potential, so you can see it mathematically as well. You can reason that it must be because it's an electron being accelerated from one plate to the other plate. So as discussed in the previous video, we understand that means it will go from lower to higher potential as it loses its electric potential energy. And so we can immediately answer the second part, or we can see from here, this is the potential difference, is VB minus VA. Now if this works out to be a positive value, as it does here, then that means VB is larger than VA. Otherwise, if VB was smaller than VA, then this would have worked out as a negative value. So we can also see from here that plate B has a higher potential. Okay, now for the second part of the question, B. Now what are we going to, what is asked here? Let's quickly see again. If the electric field is uniform and has this strength, then what is the plate separation? Okay, so what formula do I have for that relates these three values? I've got electric field and it's got a certain strength, and it's got after the separation. So now what you've got to remember is this formula. E is equal to the absolute value VBA over D. And let's just revise quickly what that means, what the context of this formula is. That is, if you've gotten a uniform electric field like that, and you've got 2 points A and B like this, then the electric field strength E is given by the absolute value of the potential difference between these 2 points divided by the distance D between them. It's a subtle point which I don't see being mentioned in the textbook. I can't remember whether we specified this in whether I pointed this out in class. It's a subtle thing. It is important that these points A and B are chosen to be in the same line, in the same direction as the electric field, or in the opposite direction of the electric field, in the same line in which the electric field is operating. So don't pick your points A and B, let's say from here there to there, because if you pick your point B there instead, and you use this formula, then you wouldn't have gotten the strength E of the electric field. You would only have gotten the strength of the electric field along this direction. So the electric field E's component in this direction, you'd only have then worked out the magnitude of that. But if you're after the electric field strength itself, then just be sure that your points A and B are operating in the same line as the electric field. But the context in which we will use this formula, this will normally be what we do, because you'll have let's say 2 plates, and you'll have an uniform electric field between them, and you'll choose your 2 points A directly from one plate to the other plate, and then this won't be a problem. In particular, this is how we chose it here, A and B, and the distance D is then the distance between the 2 plates. Okay, so let's just use this formula. What am I given? I'm given the electric field strength. So what am I after? I'm after D. So good idea to get the formula, to get what you're after on its own before you substitute any values. So what will D be if written by its own? It will be equal to VBA over E. Okay, now we can substitute. Okay, now what is this equal to? This is given to us. This is the 18.6, but it's kilovolts. Now, right, we work in SI units. Now, so let's convert it to volts per meter, not kilovolts per meter. So 10 times 10 to the 3 volts per meter, and over the actually what I just okay, this is the wrong way around. I just substituted the electric field. This is that should go below. Sorry, let's do that again. Up here goes the potential difference, which I calculated in the first part, 465 volts, and over 18.6 times 10 to the 3 volts per meter. So that's volts per meter, right? And that is equal to, like here you can see here why I had to change the kilovolts to volts. Otherwise the volts wouldn't have cancelled like this to leave only meters. Okay, so let's calculate that. 465 divided by, oh, okay, so it's 0.25. So it's that many meters. Okay, so now that is 2.5 centimeters. Okay, and that's it.